Let's start with limit as x approaches infinity of sine 2x over x. If I look at where sine 2x is as x approaches infinity, we know that sine oscillates between 1 and -1. So when you're going really far out to infinity, it's going to go between -1 and 1 forever. So it's going to go bounce back and forth. And then 1 over x is going to go to 0. So the way to do this problem is to use the squeeze theorem. So in general, we know that sine of x is between -1 and 1 for any x. So even if I double x, that's still true. Since over here we said it works for any x. Okay, now if I divide everything by x, I have -1 over x less than or equal to sine 2x over x less than or equal to 1 over x. And now if I take the limit as x approaches infinity for all of these, so just rewriting this, I see that -1 over x goes to 0, and 1 over x also goes to 0. So that means limit as x approaches infinity of sine 2x over x is between 0 and 0, so that forces the limit to go to 0. So the limit is equal to 0. Let's try a similar one, but this time let's see if we have cosine. So we have limit as x approaches infinity, negative infinity, of cosine x. Let's try that. Cosine x over 3x. So here we know cosine oscillates again from -1 to 1. So the way to do this is to write it out. So cosine is from -1 to 1. And now I'm going to divide everything by 3x. And when I take the limit as x approaches infinity for all of these, I know -1 over 3x goes to 0. 1 over 3x also goes to 0. So cosine over 3x is between two limits that are going to 0. And so cosine x over 3x, and as the limit goes as x goes to infinity, this must be 0. Okay. All right, let's move on. Let's try limit as t approaches negative infinity of 2 minus t plus sine of t over t plus cosine t. So the trick to doing this problem, like we saw in the last two, is to divide everything by t. Because I know what sine t over t, what happens to that as t goes to infinity. But if I just have sine by itself, that's going to oscillate between -1 and 1. So that means I want to multiply top and bottom by 1 over t. I'm going to distribute the 1 over t to 2. So that would be 2 over t. 1 over t times -t, that would be -1. And then 1 over t times sine of t is sine t over t. And then same thing, 1 over t with t will be 1. And then 1 over t and cosine t is cosine t over t. And that is the limit as t goes to negative infinity. 2 over t, that's going to go to 0. Sine of t over t, that also goes to 0. Cosine t over t also goes to 0. So I'm left with negative 1 over 1, and so my limit is negative 1. Okay, let's try a similar one. Limit as r approaches infinity of r plus sine r over 2r plus 7 minus 5 sine r. The goal here is to get sine over r, because then I know that the limit will go to 0. So let's multiply top and bottom by 1 over r. I have limit as r approaches infinity. Now r times 1 over r is 1, plus sine r over r. And on the bottom, 2r times 1 over r is just 2. And then we have 7 over r minus 5 sine r over r. Sine r over r, we said that goes to 0. Same thing with this. 5 sine r over r also goes to 0. 7 over r, that's 7 over a really, really big number. That also goes to 0. So all I'm left with is 1/2. So my limit is 1/2. Okay, let's try another one. Now, we're not going to be looking at sine and cosine, but let's look at just polynomials. So if I have limit as x approaches infinity, 2x plus 3 over 5x plus 7. So there's a easy way to do this, and then there's a more longer way. So let's first do the longer way, and the longer way involves dividing top and bottom by the highest degree exponent. So in this case, it's going to be x. So I'm going to divide top and bottom by x, which is the same thing as multiplying by 1 over x. So I have limit as x approaches infinity of 2 plus 3x over 5 plus 7 over x. I know that 3 over x and 7 over x will go to 0 in the long run. So in that case, we're going to have 2 over 5. Okay, so that wasn't too bad, but let's look at a better way. So back in Algebra 2, we learned about asymptotes, specifically horizontal asymptotes. So the idea behind this is, let's say, for x big enough, what's more dominant in the numerator and what's more dominant in the denominator? Well, if I compare 2x and 3, 3 is always going to be 3, so that's not very big. Versus 2x, that's going to go to infinity. So in the long run, the behavior of 2x plus 3 is closer to 2x. And on the bottom, 5x and 7, well, 7 is always going to be 7, but 5x is going to go to infinity. So that's going to be more dominant. So really, we can write this as limit as x approaches infinity of 2x over 5x. And then if we use some algebra, the x's cancel, and you're just left with 2/5. So this is a nice little way to solve these problems. But oftentimes, teachers will want you to show your work, so the top method is better to get full credit. Okay, let's try one more. Let's say we have limit as x approaches infinity of 2x cubed plus 7 over x cubed minus x squared plus x plus 7. Okay, the first step is to identify the highest exponent. The highest exponent is x cubed, right? The highest degree x cubed. So I'm going to divide top and bottom by x cubed, which is multiplying by 1 over x cubed. I'm going to rewrite this now. And then I'm going to multiply. I'm going to distribute it to 1 over x cubed. So it's 2x cubed times 1 over x cubed is 2. And we have 7 over x cubed. On the bottom, the x cubes will cancel. You get 1 minus 1 over x plus 1 over x squared plus 7 over x cubed. We see that 7 over x cubed, well, that's 7 over a really big number. So that's going to go to 0. Same thing with 1 over x squared, and 7 over x cubed. Those are all going to go to 0. And all we're left with is 2. So my limit is 2.